22 inches, and you'll see that the percentile for female is going to be much larger. So now what we want to do is we want to look at how we can use this normal distribution and the z-scores and find some percentiles, or if we're given a percentile, how we could come up with the actual x value. If you remember with our uniform distribution, we talked about uniform distribution in the last chapter. We were looking at a rectangle because a uniform distribution has that shape. If I wanted to figure out the proportion of observations that fell less than this A, it looked like that, and I just needed to use my formula for area of a rectangle. In this case, because it's that bell-shaped curve, we don't have a nice formula for our area. So what's going to happen is we're going to use either a table or the calculator to come up with the actual area. The concept is the same, and you'll notice in this problem, and this is supposed to be a less than equal to, just like in the uniform, the less than and the less than equal to are going to give me the exact same value because of the fact that the actual area under the curve at exactly A is 0. So those two things are going to be equivalent. Okay, let's look at an example here. If I have the normal distribution with a mean of 25 and a standard deviation of 5, and I want you to find the probability that I have some x value less than 35. So when I look at the graph of this, 25 goes here, 1 standard deviation would be 30, 2 standard deviation actually gives us that 35. So I'm looking at that area to the left of the 35. How am I going to come up with that area? We can use the table, and I'm going to show you that first, and then we'll actually use the calculator to come up with that area. So when I'm using the standard normal table, the first thing you want to do is write the problem in the way that they asked me to write it here. So find the probability that x is less than 35. You may have something like the probability that x is between 20 and 35, okay, as well. You want to write it in terms of the probability questions that we've been going over with the discrete random variables and the continuous random variables. Then draw a picture. So I've already drawn a picture up here. You want to look at your picture, okay? You don't need all of those values if you just want to write where the mean is, and you know that 35 is to the right of the mean, and then you can just shade in the direction that you're actually going to find the area of. Now, the key is that I need to standardize it, because in order to use my table, I'm going to need to have an actual z-score. I need to know how many standard deviations it is away from the mean. Because I gave you a nice number here, we know that my mean is 25 and my standard deviation is 5. We actually know that this z is 2, and it works out nicely. Okay? And then I can actually use either the empirical rule or I can go to my table, and I want to actually go to the table on this one so you can see how the table works. There are actually 2 pages to this table. You have the z's that are negative or to the left of the mean, and then you have the z-scores that are positive or to the right of the mean. And if you look at the actual inside this table in this area right in here, this is your area. Okay, so when you start with the smallest z of negative 3.4, which is the smallest one that you'll get in this table, you can see the area to the left is 0.0003. It's going to be a very small area. As you go up higher and higher and you actually get to 0, okay, the area is 0.5, which makes sense because of the fact that you're dealing with right in the middle. Your z of 0.5 or z of 0 gives me exactly in the middle. Okay, so what I'm looking at in this, basically in this table, is that my z is here. This area is what is given in the negative side. It's always to the left. And then in the positive side, your z is going to be to the right of 0. It's going to be some positive number, and you're going to have these areas given. So when I'm looking at the positive side, you can see at 0 I have 0.5, and these numbers just gradually get larger and larger and larger and larger until I get to the 3.49, and you'll see that this is 3.4. The 0.09 means that it's 3.49 is going to be 0.9998 because that will contain almost all of that curve. So what happens when I have z equals 2? Well, z equals 2, I'm going to go to 2 in the table, Okay, it's going to be 2.00 because I don't have any decimal after the 2. It's just 2.00. And so the actual area is going to be 0.9772. If you look at that, you'll have the 0 here. Here's where 2 is. This actual area in here is 0.9772. There are a couple of ways to interpret this. You can say that 97.72% of the values will fall below the 35, because remember my original problem was 35. X is less than 35. You could also say that 35 is the 97th percentile, meaning 97% of the values fall below it or equal to it. Or I can just look at the probability that it's falling below 35 as 0.9772. So here's another example. Here I have the summer monsoon rains in India follow approximately normal distribution with a mean of 852 millimeters and a standard deviation of 82 millimeters. Okay, so in part A, I want to look at, in the drought year 1987, 697 millimeters of rain fell. In what percent of all years will India have 697 millimeters or less of monsoon rains? So I'm looking for this. So I've written it in my terms of x. Remember, I want to convert this to a z. I want to standardize it. So what I generally do is actually standardize it within the problem, and I write it like that. So I have z is less than, here I get negative 1.89. Now I didn't look at the actual graph here first, which I probably should have done. My mean was 852. 697 is going to be down here below the mean. So getting a z-value, a z-score of negative 1.89, it seems reasonable. So with a z-score of negative 1.89, I can look at my table here, and I have negative 1.89 is going to come down here. I'll be looking at this area right here. So I get 0.0294, and what that means is the probability that I have an x value less than 694 is 0.0294. In part B, they're asking us to find the normal rainfall, which means that it's within 20% of the long-term average, or we're trying to find an x that's between 682 and 1,022 millimeters. So if I'm going to do this, I'm going to do this the same way I did the last time. I need to convert it to a z. So I say 682 minus my mean of 852 divided by 82. I'll also have to take 1,022 minus 852 divided by the 82. And you'll notice I'll get a z between negative 2.07 and 2.07. Now let's look at this diagram for this one as well. My 682 is down here, my 1022 is here, and I'm looking for the area of that region in between. This is a little bit different than the last example because I can't find this area in my table, so I'm going to have to be a little creative as far as finding the area between the two. Our table again, and in this table you'll see that I have negative 2.0, and then I need my 7, so I'm looking at the 0.0192. And since it is symmetric, this would be the area to this tail, and it'll also be the area of this tail because to the right of 2.07 is going to be the same as to the left of 2.07. And I end up getting those two areas. So how would I come up with the area in between? Well, there's two ways to look at it. I can look at it the fact that I have half from here, so that's going to be 0.5 minus that, and will give me that centerpiece, double that. Or I can look at the two tails, add those together, and since my entire area is 1, I can subtract it from that. What I end up getting here is an area of 0.9616. So how do we do these problems on a graphing calculator? Not very difficult. It's just you need to make sure that you understand where the answer comes from. In case you make a mistake, you'll understand if your answer seems reasonable or it doesn't seem reasonable. So we're going to go to that same button where you push second vars, just like we did for the binomial. But this time you're going to look at number 2 here, which is normal CDF. Okay, remember the CDF represents cumulative, and so it's everything up to that point and below. So when we use that with a probability of x less than a, all we need to do is we need to put something very, very small as our start. We always have our first number, our second number, our mean, and our standard deviation. So picking the negative 10 to the 99th is just a really small number. I could use negative 1 million or something very small, and you'll get very close to it. Negative 10 to the 99th is what we tend to use in the textbook. So for this particular, the first example that I did where they have the probability that x is less than 697, I don't need to convert to z-scores because I'm going to tell my calculator what my mean and my standard deviation is. I'm just going to put in normal CDF. I'll have the negative 10 to the 99th. I'm going to have my number it comes up to, which is 697, and then my mean was 852, and my standard deviation is 82. And you'll notice that your calculator will give you the same exact value that I got by using the table. Okay. In the second example in part B, this is where the calculator really comes in handy because I'm going to do the same thing, but because I have from a certain number to another number, I don't have to worry about the adding, the subtracting, or dealing with 1 or 0.5 like I did with the table. I actually put the 682 to the 1022 with my mean and my standard deviation, and my calculator will actually give me 0.9618. Not exactly what I got from